whatever we cover today is technically fair game. As you will see, probably won't get through all of it. And if you ask the right questions, I maybe can tell you some very vague stuff about the exam. So today we are going to talk about other sources. So with this other sources here, we'll get to it after we do our example, but we've kind of been limiting ourselves to, right, direct voltage and direct current sources, where those have been, constant. They are fixed values based off of whatever type they are. So for constant voltage sources, that has a fixed voltage value. For constant current sources, that has had a fixed current value. This is a very limited set of types of sources that we can have inside of our circuit. So we are going to introduce the other ones today. But before we do that, right, last time we talked about the loop current or the mesh method, and we talked about the node voltage method, but we didn't get through our example. So we're going to start with our example, then we'll start talking about the other types of sources. So any questions about the loop current or the node voltage methods? So we're going to start all the way over for this question, just nice and fresh. So what we want to go through and do first is go through, and we have the 3 different nodes here are identified for us. We have A, B, and C. So when we're going through and doing this, we are going to need to look at the current law for each of these different nodes. We need to go through and identify currents. While we are going through and doing this, right, we are going to make some educated guesses. We might make some 4 guesses. That's okay. But we should start, start in one location, kind of work our way through and logically guess directions instead of just haphazardly guessing like I did the first time we started this. So the probably best guess one is going to be the current through R8 here, right? That is directly after a battery. So we're going to go through and we're going to say that that one is going to be pointing upwards. For naming purposes, let's go ahead and let's have the current match the subscript of our resistor. Technically, you don't have to do this, but let's just make it easy for us to track ourselves. We'll have I8 here. If we had to guess for R7, left or right?
R7, I can't read the subscript.
That one.
Left.
Yeah, right, so it's gonna come up.
Yep.
It's gonna go one of these directions. We can guess it's left. So I'll guess I7 to the left here. Let's go ahead now. I think those are the kind of 2 easy ones-ish over here. But let's look at R6. So this one, based off of our other 2 guesses, we should probably guess it 2 is pointing to the left. We'll have I6. R5 is a little bit trickier, right? That is a ground down there. So if we look at this one here, we want to guess up or down.
Down.
Perfectly valid. So we're gonna guess that one goes down. We'll have I5. Let's look at R1, which is gonna be this one here, left or right?
Right.
Sure. Right, we don't know, we are guessing. What does that mean for I2, which is the one that is directly above it? Should probably also guess that it's to the right.
Oh, above it.
Yes, above is above.
That's the one.
Yeah.
Another one.
Well, now we can talk about R4, which is the one that you were thinking of.
Yeah.
So for this one here, right, we can go through and guess. I don't think this one here really matters which way we go through and guess. R3, we should probably guess is pointing to the right, based off of how we have I7 and I6 pointing, so we should probably guess it's that way. If we follow that idea of this current flowing around this way, R4 would be up. We are welcome to do that. We can also guess that it's down. It doesn't matter, as long as once we pick our sign, we are going with it. So who would like to see our I4 up? I4 down. Yes, we'll try it down. It's okay if we're wrong. The value is just gonna pop out. It's negative. We'll have I3 this way. Okay, so now that we've done this, we kind of have two different ways we can go through and approach it. We can write out the current law first, or we can write out each of the currents first. Doesn't really matter which way we're gonna go through and do it. Something that we talked about last time is that all of our resistors here are 1 kilo ohm. So if we want to, we can drag around 1,000, or we can just note that all of our resistant values are in terms of 1 kilo ohm. So whichever way you would prefer to do it, I'm gonna leave it as 1 kilo ohm. That way I don't have to drag around a bunch of zeros. I just know going through and doing this, I have 1 kilo ohm resistor. So that one is really 1 kilo ohm. You're welcome to drag around 1,000 instead of dragging around a 1. Both are valid. So let's go ahead and let's talk about our currents first. Are any of the currents that are given here not important for any, like just kind of overall looking at all the nodes we care about?
I2.
I2 flows into B, so it is important.
I think
Yeah, they're all in or all out of them, so all of them, unfortunately, we are going to need to deal with.
question.
It was a trick question. Sometimes that happens. So let's go ahead and with these currents here and the directions we've guessed, let's write out the current law. However, we're gonna have everything be on one side, so we'll have it equal 0 for everything. So let's start for node A. Based off of what we have here, we have in is gonna be positive, out is gonna be negative. So I1, would that be positive or negative coming into A? Let's do positive. What about I4?
Negative.
It's going in,
Oh.
so it's gonna be positive.
in my notes.
I6 is also gonna be positive. Only I5 is negative. So this will be for node A. We also can go through and look at node B. So for this one at the top here, we have only one current coming in, which is, I2 minus I3 minus I4 equals 0. You need to also go through and write out node C. So here we have 7 and 8 coming in, 6 coming out. We'll have I7 plus I8 minus I6 equals 0. So these will be the current values that we have. So in order to go through and look at these current values, we are going to utilize Ohm's law. So what is Ohm's law, where we have I on one side of the equation?
Right.
So in this particular case, when we're looking at these, all of the resistor values happen to be equal to 1. So that's going to make our life a lot simpler if we keep it as 1 kilo ohm. Just keep track of that. Otherwise, we'll have whatever our R value is time or divide by 1,000. But because each of those terms is going to have it, we can put it to the other, right? We can multiply all the terms by 1,000 and get rid of it. So it's going to mathematically work out to be the same, regardless on what units we want to use for R. It doesn't technically matter if we're gonna use 1 kilo ohm or 1,000 ohms. All terms are divided by the same value, so we can just get rid of it. All right, so we want to go through and we want to find an equation similar to Ohm's law for each of our resistors, because that's going to associate it with its particular voltage. So if we're looking at this here, let's start with I1, because it is of them. I don't want to say it's the easiest, but it's right, numerically it's first. So if I look at this node here, directly above VS1, what should my voltage be?
24.
All right, so I have 24 here. And then as I go across I1, I'm then going to have voltage A. So for current 1, this is going to be equal to 24 minus VA over my 1 kilo ohm. That is how I would solve for the current of I1. So if we look at I2, right, that is starting at this node here. It goes up, this is all still 24, I have no voltage loss as I go across an ideal wire. I go across R2, and then I'm gonna be at VB. So for I2, this is gonna be 24 minus VB over my 1 kilo ohm. I want you guys to try for I3. What would this one look like?
Where's the 24 coming from?
It's coming from our battery here. So you're gaining 24. And so at this node here, because there's nothing in between it, there'll be 24 here.
So for I3, we would lose something before.
We have lost to we're at VB to start with.
Okay,
And then how do we,
so we need to find the new.
the new. At the other side, what one would we need to consider and account for it that way?
We don't know. That's what we're trying to find out. That's why it's different. But you're saying, minus that, you drop that. So that will give you the current, if you have voltage drop to that resistance, you'll find the current, which is that. That will reflect the third.
After the drop. There's 24. No,
Or is it?
the voltage and it needs to be a voltage drop. R2 is equal to R. We know the whole resistance.
Yeah, I think. So we can't do that. Try to make those. I think. It's 3.
How much?
But you do.
I give up.
Okay. So for I3, what are right, one of them is going to be VB. What is the other value going to be? Why is it 18?
Let's see.
So if I go from B, I'm going to end up here, which is directly above my 18. So I need to figure out, is it VB minus 18 or is it 18 minus VB? That is the question that we have to answer. So in general, when we look at our change in voltage for the node method, we will do the starting location minus the ending location. So we would have VB minus 18. Questions? Okay, let's skip 4 for right now because 4 is one of the harder ones to deal with. Then 5, nice. Right here I have a ground. So my voltage is equal to 0. So what should the voltage drop be across R5? VA. Okay. We'll do 6 after we do 4. Let's look, so we're just trying to get all the easy ones out first. So let's look at our I7. I'm starting here at 18. I'm then going to VC. So I'll have 18 minus VC. And then for 8 here, right, I'm going to be starting at 10 volts and going up to VC. I'll have 10 minus VC. So, right, these are looking at, as much as we could to start with, a battery and a node. As much as we could. You don't have to do it this way. You can do them in order. It doesn't matter, but that's how we did it. Yes.
Never mind.
Okay. So let's look at 4. So for this one here, we are starting based off of the direction we've chosen, starting at B, going to A. So it should be VB minus VA. So it's always for this method, where you start minus where you end. Which means that I6 should be V what minus V what?
VC minus VA.
Right. Questions about the current equations or where we are so far?
So that's pretty much just total voltage over total current or resistance on that wire.
On that particular resistor, what does it happen to be? Yes. All right, so now that we have all of these, we have the grand fun of getting to plug them all in to these equations here. However, again, because all of these are the same exact resistance values, let's say hypothetically we were looking at node B. I'd have 24 minus VB divided by 1 or 1,000 minus I3, which is going to be whatever it is divided by 1,000 minus I4, which is also divided by 1,000. All of them are divided by 1,000. Multiply through by 1,000. It's going to cancel out. So because these are all the same, all we're really going to need to worry about is the numerator portions. So again, with this here, when we've drawn our currents on the circuit, we have gone through and we have committed to those values, those directions. Right, that has determined all the signs that we have done for our currents going in and out with the current law, as well as our changes in voltages for Ohm's law. So I ended up doing mine a little bit different, so I'm gonna have to flip back and forth a lot, that's okay. So for note A, right, we have I1. I'm gonna have 24 minus VA. I'm gonna have plus I4, which is gonna be VB minus VA. I'm gonna have plus I6, which is VC minus VA. And last but not least, I have minus I5, which is just minus VA. Equals 0. We will talk about simplifying this in a little bit. Right, but this is our first equation here. So this is taking VA, or sorry, our node A, writing all the currents out with respect to the changes in voltages, all the currents of all the currents flowing in. Again, here we've just moved all the resistors to the other side essentially and got rid of them. So we can now do node B. So this one had I2. So this is our 24 minus VB. Minus I3, which is going to be VB minus 18. And then we'll have minus I4, which is VB minus VA. And that's going to sum up to 0. And last but not least, we need to do it for node C here. So again, taking these, so we'll have I7, so 18 minus VC. Plus I8, if I recall correctly. Yeah, plus I8, which is our 10 minus VC. Then we have minus I6, which is VC minus VA. Equals 0. So these are the equations that we have. If we look at them here, there is some simplification that we can go down through and do. Right, I have a minus VA, minus VA, minus VA, minus VA.
Minus 4 VA.
Behold, we still remember some algebra. Yeah, so we'll have minus 4 VA. Sorry, we'll have 24. Not forget that if we look at the VB, we have VB once. We'll have plus VB.
1 VC.
We have 1 VC and it is also plus VC. If we look at our equation for node B, right, we're going to have 24. We do not minus VA. We have minus VB, minus VB, minus VB should be minus how many 3Bs?
3.
Yep. Equals 0. And then if we look at our final equation, we have,
Drop the minus 18.
Plus 18.
oh, oops,
Plus.
yeah, sorry, what's 24 plus 18?
22.
All right, we got 42, and then we have 18 plus 10. That's gonna be 28. Minus VA, so plus VA. 0 VB, minus VC, minus VC, minus VC. So minus 3 VC equals 0. So from here, we get to choose how we want to go through and solve this. We can do determinants. We can do substitution, do whatever your heart desires. Or whatever you're more comfortable with doing. So if we wanted to set this up for matrix, sorry, I should put the equals 0 here. Want to set this up for the matrices, we might want to go through and rewrite it as -4. Right, -4 VA plus VB plus VC equals -24. We'll rewrite this one here as VA -3 VB plus 0 VC, to just remind ourselves to put a 0 into the determinant, -42. And this one here, we would have the VA plus 0 VB -3 VC equals -28 for that. Any questions up until this point? So if we do it with the determinants, see if we did this correct, right? The characteristic determinant, which if we just write that out, right, really quick, we have -4, 1, 1, 3, negative, sorry, 1, -3, 0, 1, 0, -3. Right, that should go to 30. Or sorry, -30. And then for VA, if we wanted to go through and do this, right, we're going to replace all of our constants. So the -24, -42, -28. We're going to go through and replace all of those. The first column, keep everything else the same. What does that get us?
-426 also is a -3 in the last one.
Yep. So, right, so if we wanted to find VA, right, that would be equal to -426 divided by -30. Which should get us 14.2 volts. Any questions about VA? Or anything up until this point? Okay, so we can do the other ones as well. For the sake of time, I'm just gonna put the values. When I did VB, I got -562 over -30, which gives me 18.7 volts. And then for VC, I got -422 over -30, which should get me 14.1 volts. So those would be the voltage values for these 3 nodes.
As that, any direction you go, it'll be the same because of volt, because it doesn't divide. Or is it coming in from one direction?
So
I guess-
the voltage is just a reading at that exact location of the energy. So this is at this location, that is what it is.
So if you put like the connector thing at the.
Yeah, like kind of at, like, regardless on if you did it the up, down, or the side, you should get this value for all of it.
So if you're gonna just choose random directions to the current at the beginning, it's completely random, would that screw anything up?
As long as we stayed consistent, so. When I did my math, I have I4 going the other way. It gets you to the same thing, as long as you are keeping all of your signs correct. Cause with it here, you'll have a negative. So let's say we switch the direction of I4, this would be negative. But then when I would go through to do this, right, it'd be VA minus VB,
Yeah.
so it's a negative times a negative, so it'll cancel out.
Yeah.
If we do keep this constant.
Yeah.
So it does not matter. Any questions on 32 or the node method in general?
And those monthly values. Oh.
Nope, you're done.
Oh,
This is it. Find the voltages at ABC.
oh, you don't even need to figure out
No,
the.
that's it.
Forgot about that.
Oh, we're done.
Cool.
Yeah, so node voltage is good if we care about a specific, a couple of those. All right, so today we are gonna talk about dependent sources, which this textbook doesn't cover, but if you look at what you're supposed to cover at the University of Wyoming, right, that's assuming what we're supposed to be covering. We do need to talk about them very briefly. So we'll talk about them. We will look at the textbook that they use. If we get through that, we will very briefly start introducing some of the topics of AC sources or alternating current sources. But that's about it. So whatever we get through for the rest of this is technically fair game for the exam. So we want to make sure that if we don't get to it, it will not be on the exam. Fully.
You're saying we should ask as many questions as possible.
I think you should ask as many relevant questions as possible. Or you just push it off to exam 3, which is already probably gonna be harder anyway. So your choice. Alright, so. Everything we've dealt with so far are independent sources, right? It is a fixed value. This battery has this voltage. This current source has this current. We're going to be looking at situations where that's not always going to be the case throughout this chapter here. So what a dependent source is, it is a source that depends on the current or voltage in that particular part of the circuit. So depending on what we have, we'll determine how that relationship is determined. So we need to wait to see the 4 types of dependent sources before we're kind of ready to see how that works out. The following slides and the example we are going to do, as well as the question that is on the homework, is from the Electric Circuit 11th edition by Nielsen and Rydell. This is the textbook that, again, if we're matching the University of Wyoming, that they are currently using. I think they might be on the next edition, but same idea. So this is where it's coming from. The notation is different. So they use lowercase I for current and lowercase v for voltage. So understand that with what we're about to see here. So for our voltage source, when it's independent, if we wanted to take it away from being a battery and just have it be some sort of source that's not explicitly a battery, technically we turn it into a circle. So with this circle here, we have our plus and minus. So with it, we have our positive end, our negative end. Here we would have the direction of the electron current. So it's going from positive to negative. If you wanted to look at it for conventional, or you just flip it the other way, that's fine. And it would have some source voltage value, and it's just constant, right? It is the same value no matter what you do. You can add as many resistors as you want to the circuit. The voltage part is the same. The current becomes different. With our current sources, again, when we want to go through and generalize these, they are just a circle with an arrow in them. The arrow tells us which direction the current is going to flow. In this case, it's going upwards, and we have some voltage across it. And so here, if we look at the graphs, right on the left for our voltage source, we have the X direction is the current, so that can change, but the voltage remains constant, which is why it's a straight line or a horizontal line. If we look at the constant current source or the ideal independent current source, that is going to be the same current regardless of the voltages. So again, no matter how many resistors we put into it, the current would remain the same for an independent current source. So this is what we've been dealing with so far in this class. Nice, ideal, constant values. So not everything turns out to be this way. So as we go to dependent sources, we are going to go away from these circle and we are going to turn them into diamonds. So here we have a dependent voltage source. So we know it's a voltage source because it still has a positive and a negative inside of it. And we know it's dependent on a voltage because it has Vx here. So what this equation here is next to our source is it says Vs. So this is the source voltage for this particular source. It is equal to mu, which is just some value, whatever it happens to be, times the voltage through that part of the circuit. So Vx here is what is referred to as the controlling voltage. So this can be through that part there, it can be somewhere else. So if, right, when we go through and work on the example, we're gonna see the controlling part is somewhere else in the circuit. So just somewhere else, you'll see Vx labeled. And that says that once you find this voltage, you can now find the voltage of our dependent source. So if you're curious what the abbreviation is for one of these, it's VCVS. So that's just what it is. You can call it whatever you want, but it's a dependent voltage source where it depends on a voltage. If it depends on a current instead, so a current controlled voltage source, or a CCVS, the equation looks different. So here we have Vs. Again, this is the voltage of our source. It's equal to rho times Ix, where Ix is the controlling current, which is somewhere in that circuit, wherever it happens to be. And here we have, at the bottom, right, we see that for mu, the units are volts per volt, so it's unitless. When we have rho, it's volts per amp, such that it's gonna pop out in volts. Which one of you wants to go first? Okay,
Is IX?
oh, sorry, it's, yeah, controlling current. I take a while, yes, I made the same mistake on the next slide. Yeah,
If we were to fold those into like a circuit, how do we determine the difference? Like what, how do we know?
the equation has to be
Oh,
next to it. In reality, you would probably know what type of device you're actually putting in, and that would tell you. In circuits, diagrams, they'll have to have an equation next to it. So, but typically, instead of saying mu or rho, it's a number. It'll be some sort of fraction, like a decimal point or a fraction, times Vx or times Ix. And Ix or Vx has to also be labeled on your circuit.
Will we ever have to figure out the game?
Do what?
Figure out the rho or the mu value, which is referred to as the gain. We're not gonna do that. I'm thinking you might have a grand total of one question on one of these. But, yeah. So questions on dependent voltage sources. It turns out dependent current sources have arrows in them instead. So that's how we determine for our dependent source. If it's voltage, it'll have the plus minus. If it's current, it will have the arrow inside of it instead. And again, this arrow tells us the direction the current flows. So for the voltage controlled current source, or the VCCS, IS is gonna be the current that is created by this source. Alpha is referred to as the gain. So it is amps per volt. And we times it by Vx, which is the controlling voltage, which again, it'll be labeled in the circuit. It'll be somewhere else. We can also have the current controlled current source, or the CCS. Oh no, I got it right on this slide. So for this one here, right, we have the source value. Beta is our gain, so that is just telling us the relationship between the two currents. And IX is the controlling current, which again, it's labeled. So typically we find that first. Then we can go through and find the current from our dependent current source. Yes,
What do you mean by gain? Sorry.
gain is basically just a ratio of the two currents, or the two voltages, or the voltage and current. So it's just, typically, we're gonna see it as a decimal point, but you can also see it as a fraction for it. I don't know why it's called the gain.
So it's just a thing.
It's just a number. It's just a number, and it's going to be given to you. So the alpha, beta, mu, rho, right? Those are all the constant values. Those are explicitly going to be given to you in either the text of the question or in the circuit diagram itself. So, any questions on dependent sources, just in general? I'll wait for more of you to start. Yes.
So what exactly is the difference between a dependent source and independent source?
This one is, depending on what's going on in the rest of the circuit, will determine the dependent source actual value that it supplies. For an independent one, it's fixed. So for a 9-volt battery, it's 9 volts. Done, period, end of sentence. If you have a variable voltage source, depending on what's going on over there, it's gonna determine what my source is actually going to supply into the circuit.
So what is a real life example of a dependent source?
They are typically parts of circuits. So, trying to think about,
With the thing that contains the voltage on it, would that be?
it depends on exactly how it works. So, we'll see a circuit in a second, but, if it's gonna be a constant value, regardless of what you put into the circuit, that is considered dependent or independent, even if you can control the value.
Gotcha.
So,
So if the entire system's if it's being determined by how you have it set up, That's-
then it's gonna fall into an independent situation. So, but again, it depends on exactly what type it is and how it's affected determines what it goes into. Okay. Any other questions, just kind of in general, before we try a question with one of them? So this is the circuit here. So let's just look at it without worrying about the question right now and see what we can see from it. So on the left here, this 5 milliamp source, is that dependent or independent, and how can we tell?
it's independent because it's a circle.
Yep.
Instead of a
Yep.
diamond.
Perfect. So on the diamond on the right, is that a voltage or a current dependent source?
Voltage,
How do you know it's a voltage?
the things inside it.
Right, yeah, it's a plus and minus, that is gonna be a voltage source. If we look at the equation next to the voltage source, right, it's 150 I delta. Where's I delta?
Metal.
Yeah, so I delta is explicitly labeled. So if I can go through and I can find the current here, that is going to tell me what the voltage is for my source. So I could find that value, multiply it by 150, and that is going to get me the voltage that this dependent source is supplying to the circuit. So with this here, setting up mesh is a little bit more complicated. And by a little bit, it's just we have one extra thing we have to go through and consider. So first, we got to pick some directions. We're going to either do clockwise or counterclockwise. We're not going to mix them. So I want you to, yeah. Is that a question? No.
I was just,
We want to decide which way we want to go through and do. I delta is labeled here, so we are not going to be able to change that, but we can choose clockwise or counterclockwise. So who would like to look at clockwise loops or currents? I'd like to do counterclockwise. All right, well, of the three of you, 2 of you voted clockwise, so we will do that. So that means that we are going to go through, we're going to have 2 currents inside of this here. And we are going to have them both go not through the thing. Go like this. So we need to name these 2 currents so we don't accidentally mix them up. So what do we want to call the left mesh current? I.
I,
Sure. Then what do we want to call the one on the left then? Sure. You can call them whatever you want as long as you're consistent. So for this here, what do we know the value is for the left portion of it?
should see how I wait for my homework if you think that's bad.
I do see how you label your homework. I don't know if you know, I grade it.
I was talking about that one.
Yeah.
What?
All right, so if we're looking at the current II, this might not be the best name for it because when I'm going through and doing this, I need to look at, I'm treating this whole thing here as if it's the same current. So it's not just the 5 milliamps. I also have this I delta I have to consider. So I'll write it out. So, and then we can establish what we want to do. So if we call it II, this is going to be equal to, sorry, hold on, I need to think based off of how because I had to use last year when I did this, I used the notation that textbook used, and so I'm trying to put things together. So it's going to be equal to I1. So we're just going to call it I1 for right now. We'll talk about that in a second. Plus, for the sake of trying to keep things consistent, we can make it a capital I for I delta. That part I don't care about. With this, right, if we are just looking at the behaviors of it, this has, right, technically 2 currents. So let's write both of them out and then we'll see what we got going on. So we have ID, which is going to be equal to, why did I not write this down? Right, so for this one, it's just the currents going over on. Oh, sorry, I called this right, it's I1 there. Sorry, we're just gonna start this over. Okay, so. The current on the left is equal to ID plus I delta. Because if we think about it, in terms of looking at one of the junctions, right, I have 2 in equals 1 out. So in this case, II is equal to ID plus I delta. So from,
Could be lowercase or is it uppercase?
Said it doesn't matter.
doesn't matter.
That's how.
So this textbook, almost every textbook I've seen uses capital I, but for some reason that textbook uses lowercase I.
That's weird.
It is very weird because one of the next thing we're gonna talk about is phasors, which has independent or imaginary numbers in it. So that was J. Because they already had I for current,
We have.
not my choice. So I'm okay if we want to do this. That is perfectly fine. So we know that for the current I, as we call it now, this is gonna be equal to 5 milliamps. Because coming out of this part here, right, passing through here is 5 milliamps, which means this has to be 5 milliamps and this has to be 5 milliamps as well. So that means that I delta and ID are gonna be smaller than 5 milliamps, just in general. So I can take this and I can rearrange it such that we have I delta. That is gonna be equal to I minus ID. And so from here, I'm gonna need to go through and solve for that. So let's go through and let us look at the right mesh and figure out how we go through and do that. Before we do, are there any questions so far? So when we're looking at a mesh, which of Kirchhoff's laws do we do when going around the mesh?
Voltage, so it's
We-
I times resistance.
We're gonna look at Kirchhoff's voltage law as we go around. So we need to pick a starting point wherever we want. Let's say for the sake of argument, I'm gonna choose this top one here. So as I go across my 1 kilo ohm resistor, all right, if we go through and do this, right, that'll be plus negative, plus negative, plus negative. Right, so we'll have minus 1,000 times ID minus 150 I delta. Because here that is a voltage source, so it's just a voltage that we'd have to deal with. Minus 2,700 ID minus 5,400 ID. But I need to remember that I have the other side I need to consider as well. So if I'm looking at my left mesh, I'll have positive, negative, positive, negative. So I'd get that plus 5,400 I equals 0. While I go get my charger, I would like you guys to, for fun, write out the left mesh.
Just with the right one.
We just did the right.
Why didn't we just,
Let's say, yeah, why don't we divide?
why didn't we just make delta instead of north? That's nice.
Brett, where's it down?
To talk about one, two, why don't we use I delta in the middle?
We can talk about that in a second. I needed to go get my charger, cause
Yeah.
once that tells me it's gonna die, I probably have about 2 minutes to do that. That last 20% is not equal to the first 20%. I don't know if you guys feel that way about your old technology, but yeah. Yeah. I hope you guys had fun writing out the left mesh for no reason. What?
So those two equations are the same.
No. These are not the same.
So
This here,
the top one is for the left.
this is a junction slash current
Okay,
law,
okay.
which tells us the relationship between our currents. The reason we want to do this is, as Cody mentioned, we now have a minus 5,000 or 400 ID plus 5,400 II, which, would you know it, looks like a negative I delta. So if we're using the mesh, right, we want to keep the good practice of saying that we have the two we need to consider. But in this case, that is a defined value, which is I delta. So we can rewrite this as negative 1,000 ID minus 150 I delta minus 2,700 ID. I'm gonna pull a negative, or no, I'm gonna keep it as it is, plus, right, 5,400 I minus ID, where this here is I delta.
Wait, so if we were to do the loop method. And then do it, how I would have originally when we did that. We'd use this middle current, we do 5,400, it'd be the exact same, it'd get probably exactly the
Yes.
same. Okay.
Plus. Question. Does this help us?
Does that help us? Yeah,
How?
because now we have less variables to solve.
Okay. Do I know ID or I delta?
No,
What do I know?
wait now.
Yeah, we know
I
II.
know, I.
So instead of doing it this way, it's, even though it's more awkward, because eventually we want I delta, I need to replace this I delta with its definition. That will let me solve for ID. Then I can go through and solve for I delta. So if I wanted to use this, this equation as it is right now, I will need to go through and do the left mesh. It's fine, it works out the same way. It's just, right, we want to do it or not with the left mesh. The reason this is gonna be a little bit more awkward to write out is what is the voltage across my 5 milliamp resistor. That's a current, not a voltage. So it becomes a lot more awkward to use mesh with this on the left side. So technically, it's a little bit easier to keep it to, instead of having it as this, having minus 1,000 ID minus, right, 150. So here we plug in I delta, so I minus ID. So again, we're replacing the delta in here with this because we know II. We're gonna have minus 2,700 ID minus, or, sorry, plus, no, we'll do minus 5,400 ID plus 5,400 II equals 0. So now we have, even though we have two variables in here, only one of them is unknown, which happens to be ID. Once we have that, we can go through and solve for I delta. So do whatever rearranging you need to do first in order to go through and get here. So we should have, personally for me, I would have to go through and distribute my negative sign because otherwise I'm gonna screw that up. I'll have minus 1,000 minus minus, so plus 150 minus 2,700 minus 5,400 ID plus negative 150 plus 5,400 II, which is 5 milliamps equals 0. So assuming I plug this in correctly, I got that ID was equal to 5,550 divided by 9,250, 5 milliamps. Or this should be 3 milliamps. Assuming I did that correctly.
Which one's which again?
So now that I have that, I can utilize that I delta is equal to II minus ID, or 5 milliamps minus 3 milliamps is equal to 2 milliamps. So this would be the amount of current that flows down through the central portion of our circuit. So this is part A. Yes.
Sure.
Makes you feel any better. We did the hard stuff. Oh. Part B is find the power delivered by the independent current source, and part C is find the power delivered by the dependent current source. So you have one small step to do for B and C.
Okay.
So it's not terrible. It's just a little awkward. So any questions on A?
No.
Okay. So for B, right, we're finding the power delivered by the independent current source, and C is the power delivered by the dependent current source. We have so many equations for power. So for, let's do C first because it's easier of the two. So for, sorry, B is easier, it's the independent current source. So what, we have a couple different equations that we have for power. Pick one, and we can go through and use it. We have a couple different equations for power. And right, we can use the same power definition for both of them. It doesn't really matter. We can use P equals IV. We have Sorry, I'm trying to think about what the equations are off the top of my head. Right, V squared over R. Yeah, I squared R.
Yeah, that's.
So we can use any of these, doesn't really matter. So for example, for C, what we could go through and do if we wanted to is we can say power is equal to the current, so the 150 I delta. Because that would be, right, the current, that's the voltage times ID. So this is our the S times the current that's in that part, right? We are welcome to go through and do that. So that would give us 152 times 10 to the -3 amps times the current, which we solve as 3 times 10 to the -3 amps. So that would give us 9 times 10 to the -4 watts. And that is one of the possible ways we could go through and do this. It doesn't matter. Just pick one and go through and do it. For our other one, right, we have the current. We don't have an internal resistance, so that part's a little bit awkward for going through and doing this. So this would need a piece of information that was in the other textbook for going through and solving it. So for that, it's going, that textbook gives you some assumed values that you should go through and do. So for that, just tell you what it is, don't need to worry about it. What that textbook has is you have you with your current, so your 5 times 10 to the -3 amps. And instead of being infinite, it says the internal resistance value is always going to be 10,000 ohms. So you would go through and have that. So that is how that textbook does it. We don't need to worry about it for this class. That would get you your voltage. Then you can go through and find that the power would be equal to 0.304 watts. So don't worry about that. We're not going to be worrying about power for this exam here. The thing I would be worrying, right, is this is A, the mesh method, and B, now we have a way to go through and talk about finding, right, we found a current. That helps us go through and define a voltage for a dependent source. So are there any questions about of the other textbook, chapter 446? So really have enough time to go through and start talking about AC. Call it here. There won't be any AC stuff on exam 2. So if you guys have questions about dependent sources, though, now's probably a really good time. There is a question on it for the homework. Yes.
Page where we answer part A.
Are we, would we be, we're gonna be needing to use some sort of intervention?
I would, so if you have a dependent source question, I will tell you what method.
Oh, okay.
So like this one explicitly says use mesh.
Yeah.
So that would be the situation there. Yes.
Should it be a different number? Because,
Denominator, social media?
The numerator.
yeah, the numerator, because it's 5, 4.
Oh, that too.
Yeah.
That too.
Did I just mix up a sign somewhere? Let us check. So The thing that's harder, that textbook did a slightly different way to do mesh. Oh. Okay, I know what it is. I made a mistake when I recreated the circuit. It should be minus up here. Plus here. Which would definitely flip
Yeah.
all the signs. So. Let's see if we can,
It changes a lot.
yeah, I understand it changes a lot. I was what you would call very tired last night when I started making this, so we're just gonna color that out. And then we'll. Do it this way, so it should be minus. Oh, come on. Does not like that. I guess I'll just. Do it this way, I guess. There should be minus plus. Which then flips the signs for this here, or not, sorry, not that. Right, it flips the 150 to be positive. In all of its locations. Apologies. For that. There. You go. Yeah. Yeah, so the thing that was not fun about the last textbook is. They didn't give you any of the pictures, so I had a picture of the textbook. In the slide. Yeah, I just wasn't paying attention when I made the circuit. Apologies for that, and thank you for catching it, all of you. So. That should be correct. Any other questions about 46 or dependent sources in general? So we will talk about AC next week, but we will not have it on exam 2. So. Yeah. We'll go through that real quick there. All right, so I will see you guys on Tuesday then.
What was that? That was scary.
A sine wave is scary?
Yes.
That?
That,
It's a sine wave.
I don't like the looks of that.
Well, bad news. That's next week. And then we go, hey, isn't it cool that there's imaginary numbers associated with sines and cosines in the exponential?
I was gonna avoid sines and cosines in this course.
No, I'm gonna be honest. You thought sine and cosine wasn't important.